Welcome to CAV 2020 Keynote. Today's topic is towards robust artificial intelligence without spec-consistent machine learning, given by Pushmeet Kohli. I'm Chao Wang from University of Southern California. I'll be the session chair. During this session, please feel free to ask questions on Slack. There is a Slack channel dedicated to this keynote. And at the end of the talk, I will ask these questions, and the speaker will be able to answer that. But before the session starts, I'd like to take a moment to introduce our speaker. Pushmeet Kohli is currently a principal scientist and team leader at Google DeepMind. Before joining DeepMind, he was the director of research at the Cognition Group at Microsoft. His research revolves around intelligent systems and computational sciences, and he publishes a field of machine learning, computer vision, information retrieval, and game theory. His current research includes 3D reconstruction and rendering, probabilistic programming, and interpretable and verifiable knowledge representation from deep models. I believe it's closely related to today's talk. He's also interested in conversation agents for test completion, machine learning systems for healthcare, and augmented and virtual reality. Pushmeet has won numerous awards, and his work has also been reported on popular media outlets such as Forbes, Wired, BBC, New Scientist, and MIT Technology Review. He's also part of the ACM Distinguished Speaker Program. So without further ado, let's welcome Pushmeet and get started.
Thanks, everyone. And special thanks to the organizers. It is a pleasure to sort of be here at CAV. I don't know if many of you sort of know, but actually I started my research career back in Microsoft, working in the foundations of software engineering group, like with Yuri Gurevich, Wolfram Schulte. So like software verification and testing, particularly, are a close interest of mine from a number of years. Thereafter, I moved into machine learning, and this is what the topic of this talk will be. So I'll be talking about towards reliable artificial intelligence via spec-consistent machine learning. We all know that AI can solve key impactful problems. We have seen how machine learning has helped us in very practical problems like reducing data center cooling usage. It has also helped us in basically understanding protein structure prediction. And more recently, we have seen how GPT-3 basically allows us to really do very well on few-shot learning tasks and even code completion. But how do we check that a problem has been solved? We sort of are applying machine learning for all these different problems, but how do we sort of make sure that these problems have been really solved to what we expect them to? So just to give you an example on why this is a tricky problem, consider the following images. So these images are taken from the ImageNet dataset, which is used to train and evaluate image object detection, object classification systems. And the images that you see here depict some species of birds, cats, and some dogs. And I'm not really sure how many of you are able to correctly identify all the species that are depicted in this image, but I certainly can't. The latest image classifiers, on the other hand, are able to accurately classify all these images with 100%, like especially with these images, with perfect accuracy. So in some sense, those image classifiers are superhuman. Like at least they are superhuman in classifying these kinds of images, at least from my perspective, because I'm not really very good at like telling apart or like correctly classifying these images. The same classifiers, when you give these two images which are shown in this slide, say one is a school bus and the other is an ostrich. So what has happened here? What really has happened is that that image classifier worked really, really well on that data, but somehow does not sort of conform with the property that its prediction should be insensitive to imperceptible changes. This was some sort of an implicit requirement, like when humans sort of think about image classification, nobody would be confused between the left image and the right image, because like these are the differences between these two images are hardly perceptible to us. But in the case of machine learning systems, they can be very sensitive to even these small changes. And so if I was to think about like formally describing this specification, the specification would be that if you have any sort of extract which is close to the original image X under some sort of LP norm, and this distance is bounded by epsilon, then the prediction of the classification of these two images should be the same. And somehow the machine learning system, the superhuman machine learning systems on the ImageNet dataset was not able to satisfy this property. So what does that imply? This implies that solving ImageNet, or sort of having very high accuracy on the ImageNet classifier or some other computer vision classifier classification benchmark like MNIST, does not imply that you have solved ImageNet as image classification as a whole. And this is not just the case in image classification. You see this all over the place, not only in vision, but in also other signals like audio. If you are trying to do speech recognition, you can see that by minimally changing the speech signal, by adding some very, very limited amount of noise, you can completely change what was being recognized by the neural network. And this does not just is not limited to perceptual signals like images and speech. You can see this in even language. So here there is a sentiment classifier, and you see that even small changes to the text dramatically change the prediction of the sentiment classifier. Like even if you sort of use synonymous sort of words, it changes the predictions, and also the classifier is susceptible to small typos. This is also the case in like when we consider tasks like natural language inference, where you are trying to see whether one statement entails some other statement. So in this particular case, we see that the premise, a little boy in a blue shirt holding a toy, sort of supports the hypothesis that a boy dressed in blue holds a toy. Now, if we reduce information from the premise, like normally you would expect that the probability of entailment would go down, but in this particular case, the model does not understand that it is not actually increasing its uncertainty, but actually is becoming more confident that the hypothesis is being entailed. So it's just that these models not only can make incorrect predictions, they are also incorrectly certain about their predictions. And this is not just limited to classification systems, it's also true for generative models. So here there is a popular sort of machine learning model called the variational autoencoder, which is commonly used for representation learning. So the idea here is that you have this image XA, you will sort of learn the encoder-decoder architecture, which gives you this representation Z. When you decode it, you will get sort of a similar sort of image. Now, if you add some noise to this original input, you would expect that the encoder would give you a representation which would be semantically similar, right? And you would get maybe a roughly similar version of the output that you had, or the reconstruction that you had obtained originally. Unfortunately, you see that a completely different reconstruction is obtained. So these models are very sensitive in the representations that they produce. So like what we had seen previously, they're oversensitive to meaningless changes in the input. So how do we resolve these issues? One way to sort of resolve these issues is to take inspiration from software engineering, and this has been also been the subject of much work, even in the verification community, where we have tried to formalize what is the correct behavior for AI systems. And then we can use, once we have formalized this correct behavior, we can then think about how do we vigorously develop machine learning systems that are consistent with those specs, and how do we test compliance with those. And finally, we can also try to extend formal verification to these machine learning models. So fundamentally, what happens here is that the process of machine learning is like translating incomplete spec, and that incomplete spec is encoded by the training data of the machine learning system, because it's just like in the case of classification tasks, you have input and input-output examples, pairs of input-output examples, and that define an incomplete specification on the final mapping that you want to learn. The issue is that this data set that you have is neither complete nor sort of completely accurate, because it's sort of biased. So in order to resolve this, the idea is that can we incorporate some specifications which give us additional information about how the system should behave. So I call this sort of paradigm the spec-consistent AI paradigm. So what kind of specifications might want AI systems to comply with? So specifications which encode safety, that the machine learning model should not violate safety constraints, are robust in adversarial environments. They are reliable in the sense that they generalize to real-world variations. They know what they don't know. They understand a good notion of uncertainty about out-of-distribution inputs, for instance. And they are trustworthy in the sense that they are explainable, they are fair, and then they are private. Now, as you can sort of see, like in order to solve this problem and have AI systems which are safe, reliable, and trustworthy, there are two key questions. First, how do you even formalize these specifications? And this is not a task that computer scientists can do on their own. This is a very complicated sort of task which requires involvement by civil society, by people sort of who are experts in ethics and fairness and so on. But where computer scientists can sort of add value is by providing a language in which these systems, these specifications can be described. Once you have some sort of formal specification, then the other task from the machine learning community is develop methods that can make these machine learning systems compliant with these rules and specifications that the domain experts have specified in the appropriate language. To give you an example of how complicated the formalization of these specs is, so I will go back to my original example of image classification, and there we saw that we had an incomplete specification in the form of a training data set, which specified that for certain images, what should be the corresponding label. So you have some sort of images of cats or dogs and the appropriate label. Now, in the context of this particular sort of task, which is the MNIST dataset, you have images of handwritten digits and the corresponding label. Now, this data is sort of provide the incomplete specification, and the behavior and what this results in is basically behavior like this, where a model which performs really, really well on this task when given a slightly perturbed image. So the image at the bottom here is basically slightly perturbed from the original version, and suddenly the model is saying that it's a 3 rather than an 8. So in this particular, to avoid this kind of behavior, what we can do is we can have a specification which says that which basically says that like if the distance between any sort of perturbation from the original input is less than some distance, some threshold, then the label should be the same. Now the key question is, how do you enforce this kind of specification? But these are very simple specifications. Ideally, we don't want our model to be invariant to like these noise, small magnitude noise transformations. We want the model to be invariant to semantic preserving transformations. Like in the context of digits, you want to be invariant to color, size, rotation, brush style. In the cases of, say, face recognition, you want to be invariant to skin tone, hair color, style, and so on. The challenge is, how do you formalize such semantic preserving transformations? One way that this has been addressed, especially in the context of testing and training of autonomous driving systems, is through procedural generation, where people have tried to come up with procedural generators which can try to capture the variations, a large variety of variations that an autonomous vehicle would encounter in the real world. Of course, this has the limitation that all these sort of semantics have to be sort of hand-coded in, right, in the procedural generator. Can we do something better, or can we do something which still sort of relies on the data and does not need to specify like all things by hand? So one way to sort of deal with this is by encoding transformations through attribute interpolations, where you say that we can somehow leverage representations of the original data to create interpolations and create variations in latent space. So here you see, like in this sort of image, there are two images of two sort of faces. And what we can do is, by interpolating in the latent space, create a sort of variation which you would normally not encounter like in any sort of data. Now, of course, you can do this with any two images, and this gives you a way to capture different skin tones, different lighting conditions, different poses, and so on. So this sort of way, this is a good way of actually making sure that like different types of attributes are properly expressed in your training set, or in like as a specification, you want the model to be invariant to different sort of attributes. Of course, this can only be done in certain cases, and this is just to sort of highlight that specification learning and defining sort of proper specifications is a hard task, and it's an active field of research. So suppose we have a specification, the next challenge is, how do you build machine learning systems which are consistent with these specifications? So there are three sort of key pillars of work that need to be sort of done in this particular case. One is rigorous testing of AI systems. Given a machine learning model, can you test compliance with a specification? Developing spec-consistent AI systems, where you try to train or learn a model which is consistent with a given specification. And then finally, AI verification, where you try to formally prove that a machine learning model or a neural network is consistent with a specification. Just to sort of, I'll mostly sort of talk about the second two pillars, but just to tell you why rigorous testing of AI systems is hard, I wanted to show this particular sort of example of a navigation agent. So this is a policy for navigating in an environment. And what you see is that you like if you run this navigation agent in a 3D world, it like most of the time finds the goal. But if you systematically try to find hard cases, you will still be able to find such cases. But the probability of you finding such cases is extremely low. So it's extremely important to sort of, it's a needle in a haystack type problem, where you really need to understand what are difficult problems for the particular policy or agent that I'm trying to test. Moving to developing spec-consistent AI systems and what are the challenges, I'll go back to my image classification example and try to sort of talk about what makes it so difficult. So here's a very simple neural network which takes in as input an MNIST image, image of a sort of handwritten number. And it then takes, and it goes through some sort of linear convolutional layers, some sort of non-linear rectified linear unit layers, and so on. And finally produces some logits, which can then be used to decode what was the final result. In this case, 9. Now, if you now try to depict this particular image with this dot, and you try to see what are all the images which are in this epsilon ball around this particular image as defined by my specification. So remember, my specification was that for all the images which are in this ball, the label should be the same. So you would see that you would get this sort of pink region. So what happens as you now take this image and move it through the neural network? Of course, you will get different activations and finally the logits. But what happens to this bounding box, this sort of epsilon ball around this point? It becomes a much more it has a much more complex geometry as it goes through the nonlinear transformations of the neural network. And what happens is that when you finally sort of look at the decision boundary, you see that your original example is on the right side of the decision boundary, and therefore it will not incur any loss in the learning objective. Unfortunately, you have this region in the red, where your adversarial examples live, which are small perturbations over the original image, but are now classified on the other side, which and now lie on the other side of the decision boundary, then will be given a different label. And that is the fundamental issue why these image classification systems have these exhibit these adversarial examples. Now, what are sort of some simple ways to sort of resolve this? One could say, well, why don't you just augment your training set, and so sample some and introduce some noise in your data. So of course, what you will see is that this noise gets propagated as well, and you will find certain sort of examples which are on the other side, and then this will sort of allow you to change your decision boundary. But unfortunately, this approach, because this space is so large, this approach does not really work in completely sort of taking out all the adversarial examples. The next approach, which is in some sense sort of similar to counterexample guided sort of learning, was proposed by sort of Madry et al., where they tried to do adversarial training. More specifically, what they did is try to find examples which maximally violated this particular boundary. Like try to find sort of inputs which are in this ball but are on the other side of the boundary, and then repeatedly sort of putting in and place them in the training data. This, of course, gets you much better results, but it has sort of two key limitations. One, it is computationally expensive. And secondly, while you do get robustness to the original sort of attack or mechanism to find adversarial examples, as you increase the number of steps, or as you increase the strength of the attack, your sort of robustness decreases. For instance, this particular model had 70% robustness, 70% accuracy on the original examples. This accuracy sort of dropped somewhat if you use a 10-step sort of attack mechanism to find these adversarial examples. But as you increase the number of steps that the adversary can have, or the number of sort of gradient steps that you can take to find the adversarial example, you see that your model starts performing really starts being less robust and has an accuracy of only 29.5%. So can we be provably robust, right? Can we go to a place where we can give guarantees about the consistency of a machine learning model with a specification like this epsilon ball insensitivity specification that I had mentioned below. Now, if you sort of try to do this in the naive way, the complexity of this approach would be really, really bad. So even if you have tiny sort of images, and the size of the perturbations were extremely small, even then you would, in terms of raw compute, in terms of the raw search space, it would be bigger than the search space for the game Go. So what the community sort of worked on is basically try to sort of come up with a outer envelope of this propagated region, and this was basically done both in the verification community as well as the machine learning community, and there have been a number of sort of methods which have tried to build upon these ideas, where you now look at the propagated region and try to outer bound it. And if you now can prove that the outer bound is on one side of the decision boundary, then you can now formally prove that or the whole region does not have any adversarial examples. And a lot of research has happened into how do you make these bounds tighter so that you can get better guarantees about different machine learning models. The second approach that that has been sort of used is to use a weaker relaxation, but then incorporate it within the learning protocol. And what happens in this particular case is that you start with a sort of weaker relaxation, but over time you try to train the model such that the relaxation becomes tight. And this approach has also given remarkable sort of results in terms of accuracy and verified robustness rates. So at this point, like I mentioned, the difficulty of defining specifications and some of the technical challenges that lie in actually realizing spec-consistent AI systems in the form of testing, training machine learning systems to be compliant with specifications, and finally, formal verification. I would now want to basically give some case study examples to really sort of give you a sense of what are the how we can use these things in actual real life applications. So the first case study that I want to present is reducing bias in language models, and this is a very topical topic because of interest in large-scale language models like GPT-2 and GPT-3. So just for background, what is the language model? The language model is essentially a probability distribution over sort of over generations of text. So you give some input, and the language model is supposed to sort of say what is the completion, and this can be used for generating sort of text in an auto-regressive fashion, and you can be used for applications like summarization, question answering, and all the different applications that have been shown in the context of GPT-3. Now, while the language models are really, really powerful, it has been shown that they suffer from biases. And there's a lot of literature on essentially the language models capturing the bias that was implicit in the training data. So how can we overcome these biases? So one example is depicted in this figure. So here you have a conditioning text, an attribute, and you say my friend is a dash, and we had a grand time organizing and so on. So if you now look at the sentiment of the generated continuations that the language model produced, and you see these completions if this blank was the occupation baker versus the blank was the occupation accountant, you see that there is a dramatic there's a a prominent difference in the sentiment score. So on average, you would get positive sort of sentiment completions when the occupation is baker, uh, uh, in comparison to when the occupation is an accountant. Now, this is implicit in the training data that was used, but suppose we don't want this to be exhibited by the language model. And now you can sort of see how this kind of bias can appear in various different sort of contexts, not just in occupation, but in gender, in like ethnicity, and so on. So what you want here is basically that the sentiment of the generator corresponding to some protected attributes, whether like suppose you are looking at the generations corresponding to the male subject or a female subject, then the positivity of that sentiment should be the same, should roughly be the same. There should not be any disparity. So suppose we want to reduce this disparity, how would that work? So if that was your specification, what we have done there is we have said that the language model has to now sort of reduce its prediction loss, but at the same time, it has to reduce this fairness loss between the outputs it generated corresponding to certain sort of edits in the text. So if I say my friend from France told me dash dash dash, versus my friend from Italy told me dash dash dash, I want to make sure that the extracted embeddings and then the generations that are produced by the language model, their sentiment score should be sort of similar in average. And you can now do this not just for countries and occupations, but different names and different genders and so on. And if you use this sort of approach, you can see that the final sort of model has a much more sort of similar sentiment score rather than the original sort of model. And now this was just a specification which was operating over sentiment of the generated text, but you can think about other types of properties that people might want to ensure that are consistent across some edit to the original input. The second case study that I want to sort of talk about is on inconsistent predictive uncertainty, where the model does not know what it doesn't know, right? So, and here I wanted to again come back to the example that I had shown earlier, where which was the task of entailment, where we wanted to check whether a particular sort of sentence entails some other sentence. And we saw that if you reduced information in the premise, like counterintuitively, the model was actually becoming more certain and saying that the probability of entailment is higher. And in fact, like when we analyzed the data for this task, we saw that for 20% of the samples, 78% of the premise words can be adversarially removed while increasing the probability of the original prediction. So in some sense, as you are taking information away, the model is becoming more certain, which is inconsistent behavior. So here, what would you want to do is basically you might want to sort of say that as you sort of, if you have a reduced input like this, then the probability that you sort of assign to that sort of input is necessarily sort of smaller than the original sort of input in this particular case. And I don't have time to actually go into the details of how this is done. But like when we see this approach, when we sort of try to incorporate this specification, we see that we are much better in getting models which understand where they are uncertain and sort of are better at predicting entailment. The third case study is again sort of related to text, which is about text perturbations. So you had seen how images, when they were perturbed, like made the classifier make incorrect predictions. You can do the same sort of thing with text, and like both with synonym replacement as well as for typos, completely change the prediction of things like sentiment of the original text. So here again, we used the bound propagation method that I had shown you earlier, and we could significantly sort of reduce the amount of sensitivity to these perturbations. And if you sort of look at this model, you will see that our approach, this interval bound propagation approach, and system sort of quite dramatically increases the adversarial accuracy and the oracle accuracy both at the character level and the oracle accuracy at the word level. So the fourth case study is basically on adversarially robust representations. So representation learning is an extremely important task in machine learning, and I had shown how sort of traditional models are quite the representations that they produced are quite sensitive to these perturbations. So in order to reduce this sensitivity, we said that if there are sort of a small perturbation, if the inputs are changed minimally, like in this particular case, the representations should also be the same. So by incorporating this sort of model, we can get much better representation than to actually check whether our models are, the representations are actually more robust. What we can do is use those representations in downstream tasks, like detecting whether somebody is wearing eyeglasses or somebody is smiling, and many different tasks. And over these multiple tasks, whether detecting somebody bald or has a mustache or is wearing a necklace or has straight hair or wearing a hat and so on, you see that the traditional accuracy of a VAE model, the vanilla model, sort of is quite high. But as soon as you minimally perturb the inputs, the accuracy becomes zero if you use the standard representation. However, this our new model, which has this which produces this smooth encoder, which produces this consistent representations, it produces representations which not only have high accuracy on the original inputs, but even when the inputs are attacked adversarially or basically are perturbed by an attacker, the reduction in accuracy is not that dramatic. Like you are able to maintain accuracy to a significant amount. Finally, I will sort of just quickly talk about an interesting sort of specification from a computer science perspective. So this is sort of a model for machine translation. So a few years back, the most popular model for machine translation was a sequence-to-sequence model. And so here's the model which actually performs really well. Given this sort of input, in German, it is able to produce the correct answer. But what happens if I give it an adversarial input? It suddenly sort of goes into a loop and starts outputting sort of extremely long output, which definitely has is completely sort of rubbish and is improbable. So how do you ensure that in these variable output prediction models, that the output has a constant size, that it actually the encoder, the decoder actually terminates. So in this particular case, we wanted to have a specification that incorporated conformity to some output size constraints. So given the model M, a sample input X, we wanted to ask the question, does the model terminate in K steps for all inputs which are perturbations of the original input? And this is a sort of non-trivial sort of question in the context of analyzing these models, but we were able to show that you can actually indeed verify up to some perturbation radius. So if you take a sentence for machine translation, or if you take a image for image captioning, you can perturb that image, and up till a particular point, you can actually guarantee that the outputs that will be generated by this variable output model will be bounded to some size. So finally, I wanted to sort of touch upon one final sort of point about the specifications. So I mentioned sort of in my original slides that you can categorize these specifications in terms of safety specifications, reliability specifications, and trustworthy specifications. And I really wanted to highlight one particular sort of keyword, which is the explainable specification. and which I have not sort of spoken about in any of the sort of case studies I had mentioned. So when we think about explainability, of course, the question is who requires the explanation? Is it the user, the designer, or the regulator? And the explanation sort of is different for a user versus the designer versus the regulator. And then the other question that needs to be sort of answered is what needs to be sort of explained? How the machine learning system is making its decision, or what is the machine learning system trying to do, or why is the machine learning system making these decisions? And these are different sort of things which are subtly sort of different, and the tasks are different. So, and then there is of course the issue of if you can you explain the learned system or versus basically learning an explainable model. So in order to basically do this, I'll give an example of work that we had done a couple of years back, in which we take a neural sort of policy for sort of a driving simulator. And you can see that this neural policy, like it is quite sort of jittery in its motions. If you sort of now distill that sort of neural policy into a programmatic policy, you see that it is much smoother. So it is not only a compact policy, but it is also having sort of much sort of smoother sort of actions. Furthermore, if you take the neural policy and test it on a new track, you will see that the policy does not generalize, because it has it maybe overfit on the original sort of track, while this new programmatic policy is able to generalize very well. So why is that? I think one reason might be that there is an inductive bias sort of implicit in the program, in the DSL, domain-specific language that we had used to sort of distill or translate the neural policy into, and that gave it a sort of more robustness. So I think this is sort of an interesting direction for future research as to how can we make machine learning program in the DSL domain sort of distill or translate the neural policy sort of more robustness into a language which humans can comprehend more easily. So I'll conclude by sort of mentioning sort of key sort of challenges, and the challenges for building spec-consistent artificial intelligence are both social and technical. So on the social side, we really have to take evaluation of these evaluation of these systems beyond the static benchmarks. Currently, like most models are evaluated on the basis of their performance on some data set or some environment, and how can we now sort of extend this paradigm towards specification-driven testing of AI systems, where you also have to find consistency with certain rules and properties that the designers had in mind. Of course, there are technical challenges that come in realizing this, which is one is how do you formalize the specifications? What are languages in which you can sort of express the rich specific rules and applications that people sort of expand? And secondly, which is one is communication, what are languages in which it has been developed and has worked really well for sort of verifying and testing programs. But as you sort of move to these very large models, sort of formal verification and testing becomes extremely sort of difficult. So I'd like to conclude by sort of making the remark that like testing and debugging of AI systems will, in my view, become one of the most important problems facing the whole computer science research community. In fact, like I would sort of say that given how fast machine learning and AI systems are being deployed across the board in various different disciplines, it becomes extremely important for us to really sort of understand and capture the behavior of these models and to ensure that they are behaving appropriately, especially as now we are seeing them deployed in extremely mission critical domains like medical imaging, or in health, in the case of health, or in the case of autonomous vehicles, and so on. So with this, I'll just conclude by this credit slide, and thank my collaborators at DeepMind and sort of beyond, who shared sort of most of this work was sort of done with them. Thank you.
Thank you so much for the interesting talk. I think it's a very fascinating topic. Clearly, in order to understand this kind of a specification for AI systems, there needs to be like a multidisciplinary effort, right? So if it's a purely engineered system, maybe we can carefully specify, what's the desired behavior. But it seems that sometimes it involves human, right? Perception, bias, and all that. It veers into this social science, and how do we understand about ourselves, right? So that tends to be a very challenging part.
Absolutely, absolutely. And so specifications so I did not touch upon this, but even if you think about what is fairness, it's a whole sort of philosophical topic as to really to think about fairness. And there are a number of I'm very pleased to sort of see that there are a number of researchers who are really taking a cross-disciplinary approach in sort of capturing what are the implications, not just basically looking at dataset bias, but more generally, what are the implications of machine learning systems, and what are the fairness implications across the board. So, and that's just one particular sort of case, but there are so many different types of behaviors that we want the machine learning system to be consistent with.
So there is a question related to this specification. The first thing that you talked about is about the robustness against perturbation, right? So when you change a few pixels in an image, something changed. So I wonder if, this is a question asked by Rupsha Samantha. It's about, you have an epsilon in the definition, right? So how do you relate that to what's perceptible by a human? Say, I guess, when humans judge whether two images are similar or not, we're probably not using epsilon, right?
Yeah, absolutely. That's a good point, right? So in fact, there are two elements to this. One is basically what is the distance metric, and what is the threshold, right? So the distance metric that I was using was the LP norm, right? And this LP norm is like a completely artificial thing, right? That's not sort of describing the perceptual similarity of two images. It's just saying, like in LP norm space, like in say in L2, like in Euclidean space, what is the distance? So this is just to exercise whether current machine learning systems can even handle these kinds of specifications. But a lot more research needs to be done in the design of the metric. So we need to go towards more perceptual metrics. And the whole question of the threshold comes is again extremely important. So when I was talking about these semantic sort of specifications, so people have sort of come up with notions of procedural generation of transformations, right? And again, then the question will be like, suppose you are looking at the image of a card, right? And so you want it to appear in different colors, in different contrast ratios, in different angles. But what are the ranges? It's not clear, right? How small could it be? How big could it be? And so on. The other way is to when we were looking at sort of invariance to say skin tones. What we were able to do is basically say that there are images of various skin tones in the data set, but now by basically doing this cross product in the way that we were able to sort of use disentangled representations, we were able to capture that difference.
So there is a related question asked by Shuvendra Lahiri. So the question is, I mean, apparently we don't expect a machine learning system or any system or even human to be correct for all inputs, right? So there is this notion of which part of the inputs are more important than others. Is there any progress along this line to specify, you know, we should focus more on this region, not that region, something like that?
Yeah, so let's think about the machine learning paradigm. The machine learning paradigm is basically sort of translating this incomplete specification, which is like this set of input-output examples, into a mapping. And now people can sort of say that you can have different losses corresponding to different instances, right? You can say certain mistakes are extremely costly, and you will be penalized for them. And so that could be done in the traditional empirical risk minimization paradigm, where you're just evaluating the model on the basis of some inputs. The challenge, the extension there that we have done here is basically are saying that evaluating based on these finite set of inputs does not work, because in those finite set of inputs there are infinite number of other things where you are not testing the model, and the model might be behaving completely sort of badly. Now, if there are sort of regions in the inputs which you really, really care about, right? So either you should stress test them, right? Or you should have a way of capturing the behavior of the model more rigorously in those areas.
So there's another question that is asked by Joe Deschmo. So he had a suggestion, right? So since it's so hard to tackle the specification problem, is it possible to prepare some kind of data set where you not only have the data, but also you have some kind of annotation? For example, you could say, well, this image shows a cat that looks very much like a dog, but it's a cat because, you know, it's like certain features. Or, well, this example is put in the data set because it's used to add some noise. So to help the classifier not to misclassify or something like that. So he wonders if there's any progress along this line.
Yeah, so this is another sort of important area, and it also touches upon the point that I was mentioning about explainable machine learning systems, right? At the end of the day, what we are trying to do is basically communicate the desired behavior to the machine learning model, and we can do that by either just saying input-output examples, or by augmenting this with some formal specifications. But nobody but this dichotomy is sort of artificial. We could sort of be more fine-grained and say we will give you more information about certain inputs, right? And we will even check consistency of your outputs under those concepts. Right. So at the moment, basically, the model does not know the concept of snout or any other sort of intermediate sort of concept. It might be leveraging it internally, but it does not have a semantic word associated with it, right? But if we somehow expose it in our specification, either in the incomplete part or in the sort of formal part, we can then sort of see whether it is consistent with that augmented sort of specification which exercises these concepts.
So there's another related question asked by Caleb. I hope I pronounced it correctly. So the question is, you know, the most popular way of characterizing the robustness of image classifiers is, you know, this epsilon perturbation-based robustness. But is it possible to do it another way? For example, he was mentioning the Lipschitz continuity, right? So in the if you have similar inputs, you should have similar outputs. Is there any work along this line?
Yeah, so I think this is absolutely this is bringing up an important point. And when we sort of talk about this local insensitivity, we check this local insensitivity only around the sort of inputs in the training set, right? And the hope is that basically those inputs are far away from the decision boundary. If they are on the decision boundary, and in fact even small imperceptible changes can basically can flip the image over, then they are not valid. Sort of then the specification is not valid, right? And so at the moment, what we have done is basically we have said, okay, let's take the inputs, let's take the specification that we already have, and try to augment it, right? But like Caleb is absolutely right that is not the optimal way of doing it. It sort of piggybacks on the fact that we have input-output examples and a partial specification which we are augmenting, but there could be more sort of compact and richer ways of doing it, of encoding the specification.
I see. So Kaldeep asked a almost philosophical question, right? Is it realistic to expect systems with complete robustness when we don't expect them to be 100% accurate? So are we asking too much, along this line?
Yeah. So I think there is an element of where the error comes from, right? So some errors are because the model saw some data which is out of distribution, right? So if you train a medical imaging system and gave it a completely different pathology, like a doctor who has never seen that disease, the doctor would not know what to do, right? Then we want the doctor to be uncertain, right? We want the doctor not say, well, oh, I know exactly what is wrong with you, even though I've not seen I've not seen this sort of disease, right? We don't want that doctor. We want the doctor where it says, okay, I've not seen this disease, I'm uncertain, right? So where does that error come? Like not all errors are equal, right? Some errors are much more sort of costly than others. So when we talk about these specifications, they go beyond sort of accuracy. Sometimes they are so intrinsic, they are so important. Like, and you're right. Like in some cases, for instance, in the case of self-driving cars, we would want that like things are always true, right? In the case of there are certain applications where regardless of what is the accuracy, certain other properties need to be sort of definitely maintained. For example, in the machine translation system, I don't want your machine translation, the output to just do a buffer overload, right, attack. So of course, you can do that sort of more concretely by just clipping the results. But I'm just giving examples that you're right. But as we move towards that point where machine learning systems are behaving like humans, right? At least on the input-output examples like ImageNet, they are actually outperforming humans. And when they are confused, in fact, humans are also confused. But they are making these very silly mistakes where like some small perturbation just completely changes the prediction, right? So there we should try to improve their behavior while on the other side being happy that their accuracy is beyond sort of human accuracy.
There is another question that is specific to the second case study that you showed. This is asked by Sanjay Seshia. For the data augmentation option that the IDP was compared against, the integer bound propagation. How was the data augmentation done? Some people have observed that the effectiveness of the data augmentation can be quite sensitive to how exactly the augmentation is done. So that's why it's interesting.
Yeah, so that's a good question. Like if you think about adversarial training, you can think adversarial training is a type of data augmentation. It's a particular policy where I'm like augmenting the data specifically by maximizing the loss incurred, right? But so in that particular case, we were just doing uniform sampling, right? But like if we were doing, we could have done sort of this adversarial sort of testing. And I think in the context of that particular project, we had done adversarial sort of testing and training as well, and it did perform. Like there were some issues with why it didn't work, because it sometimes overfits. So there are complex sort of issues regarding like which method sort of tends to overfit versus generalize better. So in the context of that particular graph, you will see that we did try the adversarial training. The augmentation was more uniform sampling of the different words being removed to see whether the uncertainty is increasing appropriately or decreasing. But that's a good point.
So I think we're running out of time. So there are a lot of other questions. It seems that there are a lot of interest. So probably after this talk, we can go to the Slack channel and answer them individually. So I'd like to thank you again for giving this wonderful talk. And let's end this talk here, and then we'll move on to the offline. Thank you.
Okay. Thanks a lot.